All right, in this video, we're going to talk about section 5.1 dealing with antiderivatives and indefinite integrals. And in this section, we're going to be finding indefinite integrals. We'll also be finding particular antiderivatives, and we're going to be solving applications involving antiderivatives and indefinite integrals. Now, up until now, you've been taking derivatives functions. We've been using various rules for taking the derivatives. Now we're going to be going the other way around. This time you'll be given the derivative of the function. You have to find out what the original function started off as. So here we're looking for what they call the antiderivative. Okay. So here, many operations in mathematics have inverses. For example, division is the inverse of multiplication. The inverse operation of finding a derivative called the antiderivative will now command our attention. So a function called capital F is an antiderivative of the function f if capital F prime of x is equal to f of x. Okay, so here's some examples that we can look at here. Like if we have capital F of x is equal to x cubed, that is the antiderivative of the function f of x equal to x squared, because if we take the derivative of x cubed divided by 3 with respect to x, we will get x squared. Also note that the derivative with respect to x of x cubed over 3 plus 2 will also be x squared. And similarly, x cubed divided by 3 minus x, if you take its derivative with respect to x, is also going to be x squared. And the derivative with respect to x of x cubed over 3 plus the square root of 5, that's also equal to x squared. Notice on each one of these, if you take the derivative of a constant, it's going to be equal to 0. The derivative of a constant is 0, if you recall. So it appears that x cubed divided by 3 plus some constant c, and c is going to be any real number, that is an antiderivative of x squared. Okay. So the antidifferentiation of a given function does not give a unique function, but an entire family of functions. Okay. So when we're doing the antiderivative, we're looking for a family of functions. That's the entire family of functions. So here's the first theorem number 1, dealing with the antiderivative. If the derivatives of two functions are equal on an open interval, a comma b, then the functions differ by at most a constant. So symbolically, if f and g are differentiable functions on the interval a comma b, and f prime of x is equal to g prime of x for all x in a comma b, then f of x is going to be equal to g of x plus k. I should say capital F of x is equal to capital G of x plus k for some constant k. All right, so on the next page, let's look at an example of just this. Now, we're going to note in this example that the derivative with respect to x cubed, with respect to x of x cubed is equal to 3x squared. So here we want to find all of the antiderivatives of f of x equal to 3x squared. Well, we've already established that if the derivative with respect to x of x cubed is going to be 3x squared, then that means the antiderivative of this function will have to be, in this case, capital F of x equaling to, in this case, x cubed. But we just can't leave it as just x cubed. We have to tack on plus k. And k is a constant. All right, so now in part B, we want to graph the antiderivative of f of x equal to 3x squared that passes through the point 0, 0. and also through the 0.01 and through the 0.02. So if the antiderivative is this, capital F of x equals to x cubed plus k, let's find out what that's going to be when we do our xy table. Here's x, and this is going to be capital F of x. And in this case, through the 0.00, that means that if x is 0, then that means f of x will have to be equal to 0. Okay. And that would mean in this case here, k will be equal to 0 because f of x is 0 and x will be 0. So 0 cubed is 0 plus k will give us 0. So k will have to be equal to 0. That would mean my f of x will have to be just plain x cubed. So here, if x is 1, we're just going to select some values for x here. So for x is equal to 1, 1 cubed, or 1 times 1 times 1 will be 1. Or if x is equal to 2, 2 cubed, or 2 times 2 times 2 will be 8. Now for negative 1, in this case here, a negative to an odd power will have to be negative. So negative 1 to the third will be negative 1 times negative 1 times negative 1, which is negative 1. And then for negative 2, that's going to be negative 2 times negative 2 times negative 2, or negative 8. So let's graph this on a coordinate plane. And I'm going to use different colors here. So 0, 0 will be at the origin. 1, 1 will be to the right 1 and up 1. 2, 8 will be to the right 2 and up 8. 1, negative 1, negative 1, negative 1 will be to the left 1 and down 1. And then negative 2, negative 8 will be to the left 2 and down 8. So this is what the graph of f of x is equal to x cubed will look like. Looks like this. And forgive me for this part right here, it looks a little bit off. All right, now for, let's see, through the 0.01. So in other words, 0, 1 will be right here on the y-axis. So we know that this graph will be, well, let's find out what's going to be happening here. That's going to be x cubed, but notice it's moved up 1, so that means it'll be x cubed plus 1. Because for x is 0, 0 cubed will be 0 plus 1. That will be 1. And I'm going to use these same x values here, 1, 2, negative 1, negative 2. So for x is 1, 1 cubed will be 1 plus 1, which is 2. And then for x is 2, 2 cubed will be 8, 8 plus 1 will be 9. For negative 1 cubed is negative 1 plus 1, which is 0. And then for negative 2 cubed will be negative 8, plus 1 will be negative 7. All right, so let's see what that graph will look like. We pretty much can get an idea of what it's going to look like here. So 0, 1 is on the y-axis. 1, 2 will be to the right 1 and up 2. 2, 9 will be to the right 2 and up 9. And negative 1, 0. That's on the x-axis. Negative 2, negative 7 would be about right here. So here's what that graph will be looking like. And then finally for 0, 2, So here I'm going to draw another table for x and then capital F of x, which is x cubed plus something. So if x is 0, that means my y has to be 2. 0 cubed will be 0. For it to be 2, I had to add 2 to this function. So it'd be x cubed plus 2. And then I use my same values here, like x values like 1, 2, -1, -2. So for x is 1, 1 cubed will be 1. 1 plus 2 will be 3. And then for x is 2, 2 cubed will be 8. 8 plus 2 will be 10. And then for -1, -1 cubed will be -1, plus 2 will be 1. And then for -2, -2 cubed will be -8. -8 plus 2 will be -6. So I'm going to use a different color to graph this one. So 0, 2 is on the y-axis, that's up here. And then 1, 3 will be to the right 1 and up 3. And then 2, 10 will be to the right 2 and up 10. So that's going to be way up here. -1, 1 will be to the left 1 and up 1. And then -2, -6 will be down here somewhere. So here's what that graph will be looking like. And these are all rough sketches of the graph of f of x equal to x cubed plus 1, x cubed, and then x cubed plus 2. So now in part C, how are the graphs of the three antiderivatives in part B related? Well, if you look at it, these graphs are nothing but translations of each other, because here we're shifting the graph of f of x equal to x cubed up. So here we can just say here that the three graphs are translations of each other. Okay, they're translations of each other. So if you remember in college algebra, you talked about translations, where shifting either upward or downward, vertically or horizontally. Here's shifting vertically up. So this, the parent graph in green, the one in red shifted up one place, and the one that's in purple shifted up 2 places. Okay. All right, now let's talk about indefinite integrals and also look at formulas and properties. Here we're going to let f of x be a function. The family of all functions that are antiderivatives of f of x is called the indefinite integral. And here we use this symbol right here. This is what we call an elongated S. Okay. And actually, this elongated S actually means the sum, which starts with the letter S. So we're using that symbol as the integral of f of x dx to represent the family of all antiderivatives of f of x. And we write it like this. Here it is. There's your integral sign, and then you have your integrand, which is f of x. Your variable of integration will be dx, and it's usually depend upon what the variable is for the function is. It could be something like f of t, so that means your variable of integration would be dt, or it could be f of some function r, then that means your variable of integration would be dr. And then that's going to be equal to capital F of x will be your antiderivative. The plus c will be the constant of integration. Okay. Now, anytime you take an indefinite integral, you're always going to include plus c, that constant of integration. All right, now on the next page is just some formulas for indefinite integrals of basic functions. For c being a constant, the first one is this: if you take the integral of x to the n dn, this is just the reverse of the power rule. In other words, if you remember the power rule, when you were taking the derivative, you always had to bring the exponent in front of the variable and then copy the exponent over to the one less power. Well, here you're going to be doing the inverse of that. In other words, the integral of x to the power of n dx will be this. You're going to add 1 to the exponent, n, divided by that new exponent, n plus 1, and then include the plus c. Now, the restriction for that is this. The n, which is your exponent, cannot be equal to -1. Okay? Now, we're going to get to that a little bit later when we go to number 3, why n can't be equal to -1. In number 2, you got the integral of e to the x dx. Now, that's the easiest integral to remember because the integral of e to the x dx will be e to the x plus c. If you recall, the derivative of e to the x is e to the x. So now for the integral of e to the x dx, that's going to be just e to the x plus c. Now, number 3 is why n can't be equal to -1. Because notice an integral of 1 over x dx. That is the same as if I wrote the integral of 1 over x dx as x, the integral of x to the -1 dx. Here I'll pull the x out of the denominator. It was a positive 1. When I take it out of the denominator, it'll be -1. So it'll be the integral of x to the -1 dx. This will not work with this power rule, number 1, that I have here. So that means here, I have to write it as as ln of the absolute value of x plus c. And the restriction there is that x can't be equal to 0 because we cannot take the absolute value of 0. Well, we cannot take the natural log of 0. Okay? So for something like this, the integral of 1 over x dx, which is the same as the integral of x to the -1 dx, is always going to be this: natural log of the absolute value of x plus c. Now, number 4 and number 5 are properties of indefinite integrals here. For k being a constant, the integral of k times the function f of x dx, here we can pull the constant in front of the integral sign and write it as k times the integral of f of x dx. And then number 5, if we had the integral of the sum of two functions or the difference of two functions, f of x plus or minus g of x dx, we can take the integral of each one of those. We can take the integral of f of x dx and then plus or minus the integral of g of x dx. So we can just take the integral of each piece. So the sum of the integral of the sum or difference of two functions will be the sum or the difference of the integral of each one of those individual functions. Okay. Now I do need to warn you that property 4 states that a constant factor can be moved across the integral sign. A variable factor, however, cannot be moved across the integral sign. In other words, let's say this: the integral of 5x to the, let's say, 1/4 dx. Here I can pull the 5 in front of the integral sign and say 5 times the integral of x to the 1/4 dx. Now, on the other hand, if I have something like this, x times x to the 2/3 dx, I can't take that x and pull it out in front. That does not mean this: x times the integral of x to the 2/3 dx. I can't do that. I can only pull a constant factor across an integral sign, not a variable factor. Okay. So this will only work in this case, but not for this one. And also, the indefinite integral of a constant function with value k is k times x plus c. So if I take an integral of a constant with respect to x, here I bring the constant over and just include the x. So it'd be k times x plus c. And if you take the derivative of k, some constant times x, it'll be that constant by itself. Okay, so do keep that in mind. All right, so now let's look at some examples of taking the indefinite integrals. So here we're going to evaluate the following indefinite integral, like the integral of 10 dx. The integral of 10 dx. Now I can write this. That 10 is a constant. That means that 10 can be placed in front of that integral sign. So it'll be 10 times the integral of, let's just say dx. And then bring the 10 over. Well, the integral of dx, that's just like 1 dx. So the integral of that would just be x. So I just tack on the x after the 10. So it'd be 10 times x plus c. Since we're taking an indefinite integral, you must include that plus c afterwards. And you can check to see if you did the integration correct. So if you take by just taking the derivative of 10x plus the constant, the derivative of 10x would just be 10, and then the derivative of the constant is 0. So that means I have done this correctly. So the integral of 10 dx will end up being 10x plus c. Okay, here's example 3. Say we want to find this indefinite integral, 18, the integral of 18 to the 5th dx. Well, notice I have the constant in front of x to the 5th, that's the 18. I can pull that across the integral sign. So it'd be 18 times the integral of x to the 5th dx. Now I'm going to bring the 18 over, and here I'm going to use that power rule, which was, in this case, rule number 1, right here. By adding 1 to the exponent, dividing it by that new exponent. So, and I'm going to do this like this. I have x to the 5, and I'm going to add 1 to that, and then that's going to be divided by that new exponent, 5 plus 1. I'll put this in parentheses. So here, if I simplify this, it will be x to the 5 plus 1, which will be x to the 6, divided by 5 plus 1, which is 6. And here I can simplify this again. I can divide 6 into 18. That goes 3 times. So I will end up with 3x to the 6. And of course, we had to add the plus c, since it's an indefinite integral. So the integral of 18 x to the 5th dx ends up being 3x to the 6 plus c. Okay. All right, here's example 4, where I want to find the integral of 6 over x dx. The integral of 6 over x dx. Well, that 6 is a constant, so that 6 can be taken on the outside in front of the integral sign, so it'll be 6 times the integral of. Now, if I did that, I'm going to have a 1 in the numerator and an x in the denominator. So I have 6 times the integral of 1 over x dx. In this case, I'm going to use number 3, because I have the integral of 1 over x dx. That's going to be the natural log of the absolute value of x plus c. So in this case here, if I bring that 6 over, take the integral of 1 over x dx, that will be the natural log of the absolute value of x plus c. And that will be as far as I can go with that problem there. So the integral of 6 over x dx will be equal to 6 times the natural log of the absolute value of x plus c. Okay. Let's say I want to find this indefinite integral. And let's say I want to check by using differentiation. In this case here, I got the integral of 3x times the quantity 7 minus x dx. Now, in this case, we're going to have to first simplify 3x times the quantity 7 minus x by using the distributive property. So in this case, this would be the integral of, if I do 3x times 7, that's going to be 21x. And then minus 3x times the x here, this will be 3x squared dx. Okay. So I have to first simplify that by using the distributive property. Now I got a difference of two expressions here. Here I'm going to break this up as the integral of each individual expression. So I can write this as the integral, and I'm going to do this since I got 21x. At 21, I can pull that out in front. I'll write that as the 21 times the integral of x dx minus that 3x squared. The 3 is a constant. I can pull that out in front as well. So I have 3 times the integral of x squared dx. And now we integrate each part. So in this case here, bring down the 21. The integral of x is like x to the 1. We add 1 to the x. So if I add 1 plus 1, that's going to be 2. So it'll be x squared. And it's going to be divided by that new exponent of 2. And then minus 3 times, if I integrate x squared, I add 1 to the 2. 1 to this exponent, so it'll be 1 plus 2, which will be 3. And then it'll be divided by that new exponent of 3. And of course, since it's an indefinite integral, we're going to add the plus c to it. Now let's simplify this here. That 21 over 1 times x squared over 2, I'm going to write that as 21 over 2 x squared minus 3, and then x cubed over 3. My 3's divide out. So I'm left with just x cubed, and then plus c. So the indefinite integral for that would be 21 over 2 x squared minus x cubed plus c. And of course, if we want to check, we can always take the derivative of this with respect to x. So we should get this back. So let's see here. If I take the derivative with respect to x of 21 over 2 x squared minus x cubed plus c is what I get. And I'll have 21 over 2. But for the derivative of x squared, I bring the exponent in front, copy the x over to the 1 less power, so it'll be x to the 1, or just x, minus, for the x cubed, I bring the exponent down, that'll be 3, copy the x over to the 1 less power, it'll be square, and then the derivative of a constant is 0. Now when I simplify this, the 2's divide out, you'll be left with 21x minus 3x squared. And of course, if you factor out the 3 and the x, 21x divided by 3x will leave me with 7 minus 3x squared divided by 3x will just leave me with x, which is the same thing as this. So you know that you found the integral correctly. That's how you check by using differentiation. All right, on the next page, have example 6. Let's say we got the integral of 1 over x to the 5th dx. The integral of 1 over x to the 5th dx. Well, notice we got the 1 over 8. That's a constant. Would it be best to go ahead and pull that 1/8 out in front of the integral sign? So it'd be 1/8 times the integral of 1 over x to the 5th dx. Now, do not make this mistake by saying that the integral of 1 over x to the 5th would be ln of the absolute value of x to the 5th. That's not the case. It does not work like that. It only works when you just got 1 over x. Take a look, 1 over x, and you're taking this integral. But here you got 1 over x to the 5th. So we need to write that using negative exponents. So I'm going to write this as negative 1/8 times the integral of, and I'm going to pull that x to the 5th out of the denominator and write it as x to the negative 5 dx. So I have 1/8 the integral of x to the negative 5 dx. Now I'm going to have to use the power rule. And what that means here is this. Bring the x over, increase the power by 1 by adding 1. So that means negative 5 plus 1 will be negative 4. And that's going to be divided by that new exponent of negative 4. And then plus c. Now, when I simplify this, let's see. I'll just multiply numerator times numerator and denominator times denominator. I can write this with a negative sign in front. 1 over 8 times 4 will be 32. And then bring over the x to the negative 4 plus c. Also, I can write this using positive exponents as negative 1 over the 32 remains in the denominator. That x to the negative 4 will be sent to the denominator as x to the positive 4 plus c. So here my final answer will be negative 1 over 32 x to the 4th plus c. Now, I'm not sure how my math lab wants you to give your final answer. They might want it like this, or they might want it like this. Okay. Example 7 is finding the indefinite integral. And also, they may ask for you to check by differentiation, which we can. Let's say we got the integral of 5 e to the z plus 2 dz. Now, notice our variable of integration is dz. So let's look at this right here. We can just break each one of these apart. Since I got the integral of a sum, I can write that as the sum of their individual integrals. So I can write this as the integral of 5 e to the z dz plus the integral of 2 dz. And that is a z right there. So let me correct that. Make that z look like a z. dz. Now let's do this. I have a 5, which is a constant. I can pull that 5 out in front of the integral sign. So I'll write that as 5 times the integral of e to the z dz. Plus I can do the same thing with that 2. 2 times the integral of dz. Now let's integrate each part. Bring down the 5 here. The easiest integral, integral of e to the z dz, just like the integral of e to the x dx, will be e to the x. So the integral of e to the z, that's simply e to the z. And then plus 2 times the integral of dz, we just tack on that variable, which is z. And since it's an indefinite integral, we must include that plus c. Okay. Anytime you take an indefinite integral, you must include plus c. Now, of course, the check would be just taking the derivative with respect to z of 5 e to the z plus 2z plus c. Well, of course, the constant, we just bring over the 5. The derivative of e to the z is e to the z, if you recall, plus the derivative of 2z is just 2. The derivative of a constant is 0. So we know that we came up with 5 e to the z plus 2. So that means we did this integration correctly. All right, now let's look at example 8. This one's a little bit different here. Here we're finding the integral of x to the 6 minus 3x divided by x to the 4th dx. Okay. What we need to do here is we need to apply a rule that where we can take each term in the numerator and divide it by the term that's in the denominator. That means your x to the 6 will be divided by x to the 4th, and minus 3x will be divided by x to the 4th. So here's how I'm going to write that as the integral of x to the 6 divided by x to the 4th minus 3x divided by x to the 4th dx. And I'm going to bring over the integral of, if I do x to the 6 divided by x to the 4th, now keep in mind when you're dividing powers of the same base, you're going to be subtracting your exponent. So I'm going to bring over the x, subtract 6 minus 4, that would give me 2, minus, bring over the 3. This x is like x to the 1, so write the x down and do 1 minus 4, that would be negative 3. And then dx. Okay. Now we're going to integrate each part. Since I have the difference at the integral of a difference, I can write that as a difference of their individual integrals. So it'll be the integral of x squared dx minus, and I'll go ahead and pull the 3 in front of that integral sign. So it'll be 3 times the integral of x to the negative 3 dx. Now let's integrate each term. The integral of x squared, we increase that exponent by 1, so the x cubed divided by that new exponent of 3, minus, I'm going to bring the 3 over, increase this exponent for the x by 1, so it'll be negative 3 plus 1, which will be negative 2, divided by that new exponent of negative 2, and then include the plus c. So here, if I simplify this, this will be x cubed over 3. This minus divided by that negative will make that a plus 3 over 1 times 1/2 will be 3 halves. X to the negative 2 plus c. And I will leave it like this. But check with my math lab to see how they want that final answer to be. They might want it like this, or they might want it like this: x cubed over 3 plus 3 over 2, where the x to the negative 2 will become x to the positive 2 in the denominator, and then plus c. They might want it as one or the other, but do check with my math lab. Okay, example 9. Here we got x to the 6 times e to the x minus 7x to the 5th divided by x to the 6. And that's with respect to x. Okay, I'm going to use a different pin here. So here, each term in the numerator will be divided by x to the 6th. So I can write this as the integral of x to the 6 e to the x divided by x to the 6 minus 7x to the 5th divided by x to the 6. And all of this is going to be dx. Now, when I simplify this, your x to the 6th in the numerator and the denominator divides out. And I'll be left with e to the x. So I'm going to have the integral of, and you always carry over that integral sign no matter what, because you haven't taken the integral yet. E to the x minus 7x to the 5th divided by x to the 6. I'll bring the 7 over, subtract 5 minus 6. That will be negative 1, so it'll be x to the negative 1 dx. Okay. Now I'm going to integrate each part since I have a minus sign in between. So it'll be the integral of e to the x dx minus, and I'll go ahead and pull the 7 out in front of the integral sign. So it'll be 7 times the integral of. Now, if I write x to the negative 1 using positive exponents, that's going to be 1 over x dx. Now, let's integrate each part. The integral of e to the x dx, that's the simplest one to take. That is e to the x. And then minus, if you recall, well, I'll bring down the 7. The integral of 1 over x dx, if you recall, that will be the natural log of the absolute value of x. That's one of our properties for logarithms here. I mean, not properties. The integral of our basic function. The integral of 1 over x dx will always be the natural log of x plus c, because that's what I have here. Integral of 1 over x will be natural log of x. So my final answer there will be e to the x minus 7 ln of x plus c. Okay. Here's some more of these. Now this time in example 10, we're going to be looking for particular antiderivatives. Here we're going to be finding the particular antiderivative of the derivative that satisfies the given condition. And here we got c prime of x equaling to 5x squared minus 3x. And here's c of 0 is equal to 5,000. That means when x is 0, your c of x will be 5,000. Let's find out what c of x is going to be. Anytime you're finding c of x, that means you have to find the integral of c prime of x dx. Because here we have the derivative. We want the antiderivative. So that means we need to integrate that derivative function with respect to x. And c prime of x in this case, if I bring down the integral, c prime of x would be that 5x squared minus 3x dx. And notice I'm keeping all of this in parentheses here. And then next I will, since I had the integral of the difference of the two, I can write this as the difference of the individual integrals. So it'd be the integral of 5x squared dx minus the integral of 3x dx. And of course, that 5 is a constant. I'll just bring down the 5 times the integral of x squared dx minus, and that 3 is a constant. I can bring that out in front and just integrate x dx. So here, bring the 5 down. Increase the power by 1 in this x, so if I add 1 to the 2, I'll get a 3. So it'll be x cubed divided by 3. And then minus 3 times, that's like an x to the 1. So if I increase that by 1, it'll be 1 plus 1, which will be 2. So it'll be x squared divided by 2. And then plus c. So that means C of x is equal to 5/3 x cubed minus 3 halves. I'm going to say 3 halves times x squared plus c. Now that's just what we call the general solution. We want a particular antiderivative. That's why we have c of 0 is equal to 5,000. So c of 0 is 5,000, meaning that if x is 0, that means c of x will be 5,000. So I'm going to replace the c of x with 5,000, and that's equal to, and here I'm going to replace each x with 0. So that means this will be 5/3 times x, which is 0, that's cube, minus 3 halves times 0 squared plus 0. Now this one's going to be easy because if I cube this 0, that's 0 times the 5/3 in front, that's 0, minus 0 squared is 0 times the 3 halves is 0, plus c. And notice I'm just going to be left with the constant c, and that's going to be equal to 5,000. So my constant would be 5,000. So here I can take that c equal 5,000, substitute it for this c in my c of x function. Well, that's up here. So here's c of x, which will be the final answer here, would be 5/3 x cubed minus 3 halves x squared plus c, where I'll replace that with 5,000. So this is the particular antiderivative of the function that will satisfy this given condition. Okay. Let's say we had this. Say I want to find the particular antiderivative of the following derivative that satisfy this given condition. And that's going to be this dr dt, the derivative of r with respect to t, is equal to 104 over t to the 5th. And here, r of 1 is equal to 47. So here, what I'm going to do here is write this as a differential by putting the dt that's in the denominator over to the other side. And I'll just have dr by itself, which would be equal to 104 divided by t to the 5th dt. Basically, what I'm doing there is just multiplying both sides by dt. Now to find out what r is, I take the integral of that expression, the integral of 104 times t to the 5th dt. I'm going to do two things here. That 104 is a constant, so I'm going to pull the 104 in front of the integral sign. That t to the 5th in the denominator, if I write it using negative exponents, it'll be t to the negative 5 dt. So I have r is equal to 104 times the integral of t to the negative 5th dt. I'm going to use the power rule in this case. That means I will increase the power by 1 and divide that by the new exponent. So r is equal to 104 times t to the negative 5 plus 1 will be negative 4. And now I'm going to divide that by that new exponent of negative 4. And that will be plus c as well. Now, if I simplify this, I'm going to continue this on the next line over here. If I do 104 divided by negative 4, that would be a negative 26. So it'll be r is equal to negative 26 times t to the negative 4 plus c. And if I was to write this using positive exponents, I will put the t to the negative 4 in the denominator and make that t to the positive 4 plus c. So r would be equal to negative 26 divided by t to the negative 4 plus c. Now I have some restrictions here, or conditions here. R of 1 is equal to 47. That means x is equal to 1. The value of r will be 47. So I'm going to substitute the r with 47. That'd be equal to negative 26 times t, in this case, is 1. So it'll be 1 to the 4th plus c. Now, 1 to the 4th will be 1. Negative 26 divided by 1 will be negative 26. So I have 47 is equal to negative 26 plus c. And then to find out what c is, since it's negative 26, the opposite of that would be to add 26 to both sides. So that means your c, your constant, would be 73. Okay, so that means we can write our particular antiderivative, which will be r is equal to negative 26 divided by t to the 4th plus our c, which is 73. So r equals negative 26 divided by t to the 4th plus 73 is our particular antiderivative for the derivative that satisfies the given condition. Okay. Now let's say we had this. Find the particular antiderivative of the following derivative that satisfies the given condition. Here we got dx dt is equal to 5 e to the t minus 7, and here x of 0 is equal to 4. That means when your t, in this case, is 0, then x of 0 would be, x of t will be equal to 4. All right, so here's what I'm going to do. If I move the dt over to the other side, I'll just have dx by itself, and that will be equal to 5 e to the t minus 7 times dt. Here I'm writing this as a differential. So to find out what x is, I need to take the integral of that expression, 5 e to the t minus 7 times dt. Then we'll integrate each part since I have a minus sign in between the two terms here. I'll write this as the integral. In fact, since that 5 is a constant, I'll do this. I'll put the 5 in front and then take the integral of just e to the t dt minus, and then the 7 can go in front of the integral of dt. So that means I have 5 times the integral of e to the t dt will just be e to the t minus 7 times the integral of dt would just be t. And of course, we have to include the plus c, which is going to give us the general antiderivative. Now, we need to find out what that particular antiderivative is from this condition here. X of 0 is equal to 4. That means t is 0, and that means x of 0 will be equal to 4, or just x is equal to 4. So we substitute here your x with 4, equaling to 5 e to the t, which is 0, minus 7 times t, again, that's 0, plus that constant c. Now, keep in mind, any non-zero number to a 0 power is 1. So e to the 0 is 1. 1 times the 5 will be 5. Minus 7 times 0 is 0. Now go and add that, plus c. So that means I have 4 is equal to 5 plus c. And to find out what c is, we have to subtract 5 on both sides. So that means c is equal to -1. So our constant that we're looking for is -1. So we just substitute that into this, general antiderivative. That means I'm going to have x is equal to 5e to the t minus 7t plus -1 would be -1. So that's our particular antiderivative. X equals 5e to the t minus 7t minus 1. Okay. And here's another one of these. Well, we're not looking for an antiderivative here. We're just looking for the equation of the curve. Here we're going to find the equation of the curve that passes through -2, -33 if its slope is given by dy dx is equal to 12x squared minus 4x for each x. So in this case here, dy dx is equal to 12x squared minus 4x. And if I was to write this as a differential, that would mean dy is equal to 12x squared minus 4x, now be in parentheses, times dx. And then to find out what y is, we just take the integral of that 12x squared minus 4x times dx. And of course, we can integrate each part since we have a minus sign here. So it'll be y is equal to, I'm going to pull the 12 out in front of the integral sign. So I have 12 times the integral of x squared dx minus, now I can pull the 4 out in front of the integral sign, and I'll have an x dx, the integral of x dx. Now let's integrate. Bring the 12 down. Using the power rule, I'll increase the power by 1, so it'll be x to the third divided by that new exponent of 3 minus 4 times. For the x to the understood 1, we increase that by 1, so it'll be x to the second divided by 2, then plus c. Now if I simplify this, 3 goes into 12 4 times. 3 goes into 12 4 times, so it'll be 4x cubed minus, and of course 2 goes into 4 2 times, so it'd be 2x squared plus c. So that's my general equation there. But we have this point, -2, -33. In other words, your x is -2 and y is -33. So the x and the y will be replaced with those values. So this y will be -33 is equal to 4 times x, which is -2, and that's cube, minus 2 times x, which is -2, and that's going to be squared, plus c. So I bring this -33 down. -2 cubed is -2 times -2 times -2. That's -8 times the 4 in front will be -32. Minus -2 squared is -2 times -2. That will be 4 times the 2 in front will be 8. So I have a -8 and then plus c. Now, if I do -32 minus 8, I would get -40. So it'd be -33 is equal to -40 plus c. And then to solve for c, I have a -40. That means I need to add 40 to both sides. So that means I'm going to have c is equal to 7. And then I'll replace that C in the general equation with 7 to come up with the equation of the line of the curve that passes through -2, -33. So it'd be y is equal to 4x cubed minus 2x squared plus 7. So that's the equation of the curve that passes through the point -2, -33 with a slope given as dy dx equal to 12x squared minus 4x. Okay. All right, the last example, number 14, is an application problem that deals with indefinite integrals. Let's say monthly sales of a particular personal computer are expected to decline at the following rate of S prime of t computers per month, where t is the time in months and S of t is the number of computers sold each month. So here's the derivative. S prime of t is equal to -10 to the 10t to the 2/3. S prime of t is equal to -10t to the 2/3. The company plans to stop manufacturing this computer when monthly sales reach 500 computers. If monthly sales now, which is going to be t is equal to 0, are 920 computers, find S of t. How long will the company continue to manufacture this computer? Okay, so now we know what S prime of t is going to be, or what S prime of t is. -10 times t to the 2/3 power. So to find S of t, it's going to be the integral of S prime of t dt. And in this case, we take the integral of S prime of t, which is, of course, -10 t to the 2/3 dt. And since -10 is a constant, I can pull the -10 out in front of the integral sign and just say -10 times the integral of 10 to the 2/3 dt. So I'll bring the -10 over. For the integral of t to the 2/3, we add 1 to the 1 plus 2/3. We increase the power by 1. So up to the side here, if I do 1 plus 2/3, that'd be 1 and 2/3. But as a improper fraction, if I do 3 times 1, that'll be 3 plus the 2, which will be 5. So it'll be 5/3. So I have t to the 5/3 now be divided by that new exponent of 5/3. And then, of course, since we're dealing with an indefinite integral, we're going to add the plus c. All right, now, here's what I'm going to do. Bring this -10 over. The reciprocal of 5/3, that's in the denominator. I can take its reciprocal by flipping the denominator, flipping this fraction. The reciprocal of 5/3 will be 3/5, so I have -10 times 3/5 times t to the 5/3 plus c. Now, if I divide 5 into -10, that's going to be -2. And then -2 times 3 would be -6. So it'll be -6 times t to the 5/3 plus c. Okay. Now, let's find of course, the particular antiderivative. Here we're told that t, monthly sales now, which is, of course, t is equal to 0. We have 920 computers, so that means S of 0 is 920. Now we'll bring down S of t here. So that S of t will be replaced with 0. I mean, not with 0, with 920. T will be substituted with 0, so it'll be negative 6 times t, which is 0, t, which is 0, and then that's raised to the 5/3 plus c. Bring the 920 down. 0 to the 5/3 power. That's 0 times negative 6, which is 0, plus c. So that means c will, your constant will have to be 920. So S of t, the particular antiderivative here, would be negative 6 t to the 5/3 plus 920. Okay. Now, the other part of the question is how long will the company continue to manufacture this computer? Now, we are told that the company plans to stop manufacturing this computer when monthly sales reach 500 computers. So that means your S of t will have to be equal to 500. S of t will be 500. So I'm going to substitute S of t with 500. That's equal to negative 6t to the 5/3 plus 920. Now to solve for t, or to get this exponential part by itself, we need to subtract 920 from both sides. So that means I have negative 420. I have negative 420 equals to negative 6t to the 5/3. And then the next step would be to divide both sides by negative 6. So that means I'm going to have t to the 5/3 equaling to 70. Because negative divided by negative will be positive. Now to get t by itself, I'm raising it to the 5/3 power. What's the reciprocal of 5/3? It will have to be to the 3/5. So t to the 5/3 will be raised to the 3/5. And this 70 will be raised to the 3/5 power. All right, now to solve for t, of course, 5/3 times 3/5, that gives me 1. So it'll just be t by itself. But on the left side, I got 70 to the 3/5 power. So I'm going to need to use my calculator to come up with the answer to this. So let me clear this junk out. And in this case here, I might need to, okay, there we go. Here's what I'm going to do. Left parentheses 70, then close the parentheses. For the exponent of 3/5, I'll use the hat key and do 3 divided by 5 for 3/5. Now, really, you don't need to use the parentheses around the 70. Then if I hit enter, let's say I want to round this off to the nearest whole number. Okay, so 12.7 to the nearest whole number would be 13. And in this case here, the T represents the number of computers per month. So the time is going to be in months. So if the company plans to stop manufacturing this computer when the monthly sales reaches 500 computers per month, then it's going to be like 13 months that they will continue to manufacture this particular computer. So T will be equal to 13. Okay. All right, so that does conclude this video in section 5.1 dealing with antiderivatives and indefinite integrals. Feel free to reach out to me if you have any questions about any of the homework problems that are in my math lab or any of the examples that were presented in this video.